I appreciate it. You said you would.
Accidentally, I did it off of primary.
The back one.
Is that it? Alright. You're
What?
cheating.
Oh, my shit.
Wait, there's one dude. Yeah. The Fargo.
No, hell no.
Yeah.
How do I have 5 girlfriends?
Oh, well, how? You tell me.
Because I don't.
You are fine.
Show me proof I have 5. Show me proof now.
Open your dark WhatsApp.
Have WhatsApp.
The dark web.
Have 5 girlfriends.
The dark web Snapchat. What? Yo, give me a pill right now.
You have enough.
I do. So what's your Thanks. I'll take a look.
Yeah.
We need to close the gate.
No, I've been running today. I need my body.
Get the gate through. Okay, go right now before Autumn goes out, because it's wide open.
Alright, got it.
Let's go to the gate. No, the gate, the main gate is wide open. If you go grab that for me, please.
Got it.
Thank you.
You keep putting pieces like that.
Oh, shoot. Get it? Take your coinage, son.
Yeah, maybe more.
Who's gonna go?
Yeah, it's fine. I'll share with him.
Where did I put my car?
I appreciate
Oh, it's on the counter over there.
It's so
Yeah.
I know, right?
If you have to on the back deck, you might want to put them on the front porch because it looks like it's gonna rain more and they're gonna get wet. If you want to put them out front where they'll be covered, feel free to do that.
What?
They still.
Yeah, next week.
How are you?
I'm pointing.
How are you?
Yeah.
The boys got a hold of that this morning.
I got an updated video.
You did?
Yeah, with the actual dominoes.
Oh, so excited.
Whose backpack is that? No idea. Emma's. Did she? I think she left.
Let her hold that.
Yeah.
It's not like her.
It's so good.
That is so good.
I'm so happy that it's working. We put in a few little things. I put it underneath the deck. I don't know where you want to.
That's fine. Totally fine under there.
It's not good. How about you? Yeah. You have to. It's working. I already got the sword energy. I already got all the energy. And we don't. You ever recreate it? No, one paper bun.
Always.
Spoiled, rotten, no.
I had the.
Daddy,
Mhm.
one more left, no idea.
Oh, no.
That one's tricky. I got everything except one. There. No, I'm gonna go back.
All right, I don't know how well I did, but that thing's hard to scramble.
Oh, you're so cute.
Spoiled. The word you're looking for is spoiled. So spoiled. All right, did everybody feel like they made a little progress today?
Yes. No.
Okay.
Yeah.
Well, if you didn't hear me before, I said, if your shoes are on the back deck, you may want to put them on the front porch because it's probably gonna rain in the next little bit. I mean, I'm surprised we survived it. Our gates shut, our gates shut. All right, good. So
I have my shoes.
don't move them to the front porch where they're covered. You know what I mean?
Okay.
On the back deck, they're just gonna get wet. And then if you don't have another pair, you'll be walking around in swamp shoes. Not fun. Drew, are those yours?
Nope.
No, somebody else's shoes are out there? Nobody else wants to move those shoes out of the rain?
Mine are inside.
Okay, there you go. Well, somebody's shoes will be wet. Don't know who. Changes like this in my shoes.
What does it look like?
Those are yours? No? Are they getting good and wet? Cause it's starting to straight up rain. Yeah. Yeah, it is.
I just saw those and I was like, ah. So they're gonna be wet.
Maybe less wet, cause I put the little shoe mat over top. Somebody on their way out will be like, oh yeah, it was mine. We talked about shoes. Silly. All right, well, we're gonna go ahead and roll. And this lesson, if we finish it, and we should, then we'll go to some review, okay? Some exam review. Try getting us familiarized good and early. Have y'all started to look at the review yet?
Yeah.
Anybody?
I flashcards.
Good job. I love it. All right. So we're just real quick touching. What's my drink over there? We're just real quick touching chemistry, like I said again. Thank you. All right. So this morning, a friend had tagged me on Facebook in a meme. And the meme said something to the effect of, public school teachers, now's the time to quit. You can homeschool 10 kids and charge for it and make $130,000 a year. Yeah, right? And I was like, yeah, it doesn't matter. I said, yeah, well, those salaries are a little off. But somebody commented on the meme. She tagged me in the meme. And somebody commented on it and was like, yeah, but I know teachers pay for a lot of stuff for their classrooms, but like, who's gonna pay for the janitor? And who's gonna pay for the desks? And I'm like, okay, I have to comment now. Desks? We don't have desks. So I had to explain. I'm like, y'all don't understand what homeschool looks like. It doesn't look like public school home. That's what I was like. You get right on it. Or the floor. We have plenty of people who sit on the floor for class. So I had to kind of explain to her how we do things because people can't visualize it if they haven't seen it. So, you know, it just kind of made me giggle. All right, so let's do this. We've only got one more lesson, right? After this one.
Next week's review, right?
Next week we'll do real quick, the lessons real quick, and then it's review. All right, so when learning about chemical reactions, it's important to remember this law that matter is never created nor destroyed. That law is what? PJ.
Wait, what?
What's this law that matter is never created nor destroyed?
The law of mass.
Law of conservation of, not mass, but look close.
Matter.
Matter, right, okay. So what does happen to matter? Yeah, go ahead, Bailey.
It changes form.
It
whether
changes
it
form.
blends into- Which then it's still there.
Right.
Still energy or, okay, in this case, it would be changing form.
Changes
like-
form, that's what we're looking for,
yeah,
yes.
Like solid, liquid, liquid, solid.
Or changes phase. So matter is never created nor destroyed. it only changes form. Now keep this in mind with chemistry too, because with chemical reactions, sometimes you're just creating new substances, but the matter that those substances are composed of is the same, right? Is the same matter you started with, the same amount. You're not creating or destroying matter. You may be creating substances, but you're using the same building blocks. So this is our law of conservation of matter. Now, you have to remember that matter is anything that has mass and takes up space. So is there matter in my hand at the moment? Yes, what is it? Air, gas, whatever, right? All right. So keeping that in mind, we're going to apply this very similar law. What's the similar law? That's the one that you hit on first, PJ, that in a chemical reaction, what else is neither created nor destroyed? Not matter, but you got it, mass. Not matter, but mass. Okay. And what do we call this law? Law of conservation of mass, right? And mass is the same thing. It's neither created or destroyed. It kind of can change. It influences force and things like that. Like we've been through that, right? All right. So this is the quick video for today. It's a quick one, but it's a good question. Yeah. Why do chemicals react?
Why not?
Yeah, and next year they're going to talk about entropy and enthalpy, and we're really going to talk about those next year. She remembers. Yeah. Yeah. This gives you an idea of why it happens to begin with.
You know how sometimes you go to bake a cake, but your bananas have all gone rotten, your utensils have rusted, you trip and pour all of your baking soda into the vinegar jug, and then your oven explodes? My friend, you and your chemical reactions have fallen victim to enthalpy and entropy, and
What is
boy
wrong
are
with
they
you?
forces to be reckoned with. Now the reactants are all products. So what are these E words, and what's their big idea? Let's start with enthalpy, an increase or decrease of energy during a chemical reaction. Every molecule of chemical potential energy stored within the bonds between its atoms. Chemicals with more energy are less stable and thus more likely to react. Let's visualize the energy flow in a reaction, the combustion of hydrogen and oxygen, by playing a round of crazy golf. Our goal is to get a ball, the reactant, up a small rise and down the other much steeper slope. Where the hill goes up, we need to add energy to the ball, and where it goes down, the ball releases energy into its surroundings. The whole represents the product or result of the reaction. When the reaction period ends, the ball is inside the hole, and we have our product, water. This, like when our oven exploded, is an exothermic reaction, meaning that the chemical's final energy is less than its starting energy, and the difference has been added to the surrounding environment as light and heat. We can also play out the opposite type of reaction, an endothermic reaction, where the final energy is greater than the starting energy. That's what we were trying to achieve by baking our cake. The added heat from the oven would change the chemical structure of the proteins in the eggs and various compounds in the butter. So that's enthalpy. As you might suspect, exothermic reactions are more likely to happen than endothermic ones because they require less energy to occur. But there's another independent factor that can make reactions happen: entropy. Entropy measures a chemical's randomness. Here's an enormous pyramid of golf balls. Its ordered structure means it has low entropy. However, when it collapses, we have chaos everywhere, balls bouncing high and wide, so much so that some even go over the hill. This shift to instability, or higher entropy, can allow for reactions to happen. As with the golf balls, in actual chemicals, this transition from structure to disorder gets some reactants past the hump and lets them start a reaction. You can see both enthalpy and entropy at play when you go to light a campfire to cook dinner. Your match adds enough energy to activate the exothermic reaction of combustion, converting the high energy combustible material in the wood
If only that were that easy.
carbon dioxide and water.
Yep.
Entropy also increases and helps the reaction along because the neat, organized log of wood is now converted into randomly moving water vapor and carbon dioxide. The energy shed by this exothermic reaction powers the endothermic reaction of cooking your dinner. Bon appetit.
You get the whole bun and mustard and everything. I'm not sure that would be very tasty.
Hot dog shaped mushroom.
It could be.
There's a really weird shape.
That's true. I've seen a lot lately. All right. So in a chemical reaction, what are we breaking or forming? Okay, Yusuf. Yeah, specifically, Asher?
Bonds.
Bonds, that's right. Okay. We are breaking or forming chemical bonds. All right. What does that say? Ooh, hang on, I turned this around the wrong way. I'm not gonna be able to find Emily or Drew because they're hiding in the back. All right, so breaking bonds requires energy, but forming bonds releases energy. And that's very important to remember. Okay, so if you break a bond, you have to have energy to break it. And if you're going to form a new bond, it's going to release energy when it's formed. All right, so keeping that in mind, if energy is absorbed by a reaction versus if energy is released, and energy is typically, we're talking about heat, usually. So in this case, if energy is absorbed by a reaction, we call it endothermic. Energy goes in endo, okay? And this means that your product is going to feel colder than its surroundings. So who can think of an example? Bailey, you got an example?
The glass.
The glass, what about it?
It feels colder than everything else around it.
Right, but that's not a chemical
No,
bond.
that's
Yeah,
just, it feels colder.
it does feel cold.
The cold pack.
There you go. Great, she's got it. Okay.
Or the heat ones.
Yeah, you ever had the little ice packs that you use if you get a boo-boo and they give you a little, you pop the little bubble in it and you shake it, it rattles around and you put it on your little boo-boo. Back when I worked at the school and I was in the front office, I swear the kids just wanted the sensory input of the cold ice packs because everybody had an injury all day long. Yeah, all day long. I'm injured. I need an ice pack all day. So it feels colder than the reactions. It's endothermic. Shh, you guys, you chattered a lot last week. Let's not repeat it, okay? Now, if it takes energy out, puts energy out, it is exothermic, okay? And that means that it's going to feel hotter than its surroundings. So another example would be those same little things that you use, but like the gloves, the hand warmers that you put inside your gloves. You ever seen those? Like, it's the same little thing. You break the little pouch, it's nice and warm. You can put them in your pockets. You can put them in your gloves. So there you go. So endothermic feels colder and it takes in energy. Endo means in, right? Exo means out. An endoskeleton is what we have. An exoskeleton is what a wasp has, right? Our skeleton's on the inside in. So exothermic is going to feel hotter. All right, so let's look here. You have two main parts of your chemical equations where you see a chemical reaction written out, all right? And we're going to do this a lot next year. You're going to get really used to it. So you have a reactant, which is the part that goes that undergoes the chemical change in a reaction. All right, so when you have a reactant, you have a little arrow in a chemical equation. That means this shows the change. It's read as yields. Where do you find the reactants? To the right or the left of that arrow? Who knows? What are you saying, James? To the left, yes, because you read left to right. So it's the first thing you see. So it's going to be to the left and it's going to look like that. Reactants, yields, products, just how you read it. So if that's the case, then you would expect your product, which is what's formed in the reaction, it's going to be on what side? Everybody.
Right.
All right. Okay, it's going to be on the right side because that's how we read. It's what's formed. Reactants, yield, products. All right, now, chemical equations. We're going to look at an example, okay, of two equations. We're going to really look at all the details, all right? So the chemicals we're going to use in these two equations are only carbon, hydrogen, and oxygen. We're not going to use anything else, okay? Those are the only elements that are going to be involved in the substances we're going to break down and create, all right? There they are. So what's this? What's CO right now? What is that? Does anybody know what compound that would be if it's just like this? Do you know? Do you know? Carbon.
Carbon oxide?
Carbon monoxide, yeah. So right now, that's just carbon monoxide because it's just CO, one carbon, one oxygen, right? So we're gonna change it in a minute. And we're gonna change it by showing things like coefficients. Right now, it's just one molecule of carbon monoxide. It's one carbon, one oxygen. But coefficients tell you how many of each of these molecules is in your substance. So For example, well, let me ask you this, where are you gonna find a coefficient? Where will it be physically? Bailey? Before it, right, okay, so in this case, here they are. They're all sixes. That's interesting. So now how many molecules of carbon monoxide do I have? I have 6 molecules. I have 6 carbons and 6 oxygens. If a unit of carbon and oxygen, that's 1 carbon monoxide. I happen to have 6. Okay, that's a coefficient. Now, if I have a subscript, where do you think I'm going to find a subscript? What do you think? On the bottom. That's exactly where I'm going to find a subscript. And a subscript is going to tell me how many of each element. Right now, we only have 1 of each element, right? We have 1 carbon, 1 oxygen, and then 6 of those together, right? But we don't have any extras subscript-wise until we put in the subscripts. Okay, now we have subscripts. So is this carbon monoxide anymore? No, what is it now? Carbon dioxide, and how many do we have? 6. Okay, so let me ask you this. In this molecule, these molecules, that substance, how many oxygens do I have?
Oh, that one,
right here. Do I have 2? I have 12. Why do I have 12?
Because there's 6.
Because there's 6 molecules. Okay, so from just in this one, we're not looking at the rest, we're just looking at the carbon dioxide. With all of my carbon dioxide, I'm going to have 6 oxygens involved, right? Because now it's carbon dioxide. Are you questioning? Oh, we're getting there. He's perceptive. He's looking ahead. All right, so the arrow is going to read as yields, okay? So you're going to read it like this. 6 molecules of carbon dioxide plus, what's the next one going to say? 6, yes, 6 molecules of water, yield, and there's where your energy is going to come in. You can note where your energy comes in. In this case, it's sunlight. Yields what? What is that? C6H12O6. That's the reaction. What's that molecule? C6H12O6. Glucose. Good job. James has got it. All right. So it's 1 molecule of glucose, C6H12O6 plus what? 6 what? Tell me, guys. 6 molecules of oxygen, which is 12 individual atoms, but it's 6 molecules of oxygen. And then the bottom one is going to be what? One molecule of glucose plus 6 oxygen molecules yields 6 molecules of carbon dioxide plus 6 molecules of water. And when you look at it, you get your energy over here, and it's coming out in the form of something we call ATP, which we'll get to more in biology, but you have the reactants on the left, the products on the right, right? There it is. So what do we notice about these 2 reactions? They're what? You said it, James, say it. They're reverse, right? They reverse one another. Does everybody agree that these reactions are like the reverse of each other? Okay, so if the first one's photosynthesis, then what is the second one going to be? Do we know? Do you know?
So that says endothermic, so the next one is exothermic?
The next one will be exothermic. You're right about that. Energy's coming out. See the energy coming in, energy going out at the end. So what do you think, Bailey?
Respiration.
Very good. There's our photosynthesis. And that one would be cellular respiration. Where do we have aerobic cellular respiration? James? In all of your cells, every one of them. So
You said souls.
in my soul is respiring. No, your aerobic cellular respiration. This is the process by which you utilize energy from, you're utilizing chemical energy that you're producing with what? With your breaking down of sugar. And if you look right here, this is what you breathe, this is what you eat. You need to do both to live, right? So you eat, you breathe, and then where does this go? Where do these go? These reactants. Yeah, in the atmosphere, how? When you exhale, what do you exhale? Carbon dioxide and water. You know you exhale water because if you go outside on a cold enough day and you breathe out, what happens? You get your vapor cloud in front of you, so you know you do. So these are opposites, exactly. All right, so when we start describing reactions, chemical reactions often involve large numbers of small particles. So chemists use a unit called what? Milo. That's it, Milo, that's our mole. And we use our moles to measure large amounts of a substance. Does anybody happen to know what the number is for moles? Do you remember? Do you know?
6.32 times 10 power to the
6.02. Yep, 6.02 times 10 to the 23rd. That number has a name. It's called Avogadro's number. Yet another cool scientist. Avogadro's number, not avocado's number. Avogadro's number. There are some really cute like little t-shirts with like little anthropomorphized avocados on them, holding up little signs that say 6.02 times 10 to the it's cute. But anyway, all right. So in chemical reactions, the mass of what two things, Emily?
reactant product.
Yes, can be calculated by using a balanced chemical equation and the molar mass. And we will be learning how to do that next year. We'll be doing it in lab. It's actually a lot of fun. So there's our little mole. You'll see him again next year. Bye-bye, cute mole. So here are some ways you can tell if a chemical reaction has taken place. What are some signs? All right, so the first example we're going to show you is this. Does anybody want to take a stab at what that might be showing?
Colors.
Actually, Caitlin, what do you think?
Color change.
Color change is exactly right. Okay, so if a color change has taken place, you have a example of a chemical reaction. Okay, who can give me an example of a color change that you see sometimes? Do you want to go for it, Lucas?
The rainbow?
That one's not a chemical reaction, though. It's a good. Usher?
Soap and milk.
Soap and milk. What happens with soap and milk?
Oh.
Color? Really? What color? I've never seen it. Don't know? Okay, who else has another one, James? Crust on bread is oxidation, yes.
Lead, nitrate, and potassium iodide.
Lead nitrate and potassium iodide, what's it do?
Makes like these weird, it's like a double, it does a double replacement.
Oh, okay, yeah, we're getting to those. Does it change color?
Yeah, it becomes yellow and it switches.
Okay, Jordan, do you have one?
When fall comes, the leaves change color.
Great example. When fall comes, the leaf changes color. And what happens there is actually you're seeing there is chemical reaction involved, but the chlorophyll is fading away and the other pigments that are underlying it are now visible. Liam, what you got?
Chameleon.
Chameleons, yeah, that's a really good example. Or scuttlefish? No. Cuttlefish. I'm like, what's a scuttlefish? A cuttlefish, yes, my brain died on me for a minute. Cuttlefish do it too. Caitlin, you have one?
Food coloring.
Sometimes it depends on the food and the type of food coloring can be. And one more.
Specific and basic reactions when you add the.
Indicators, what you're talking about. Yes, we actually use indicator in lab that tells us it's a pH indicator. Phenolphthalein we use, bromothymol blue we use, we'll be using them in lab next year.
I believe the blue is also used to treat illnesses in fish tanks.
It might be, it could be.
There is a specific something
Mhm.
blue and that may be what it was.
I know what you're talking about. I don't know if that's what's in it, but I know what you're talking about. All right, so color change is definitely one. What would this one be? Chloe. Odor. Okay. Why do your shoes stink? And don't pretend like they don't. You know they do. You know they do. Asher, why do your shoes stink? Because of what? Wizardry? Oh, come on. Caitlin, why do they stink?
Because.
Puberty? Yeah, that could be part of it, Emily. Sweat, and what gets in there? What's causing it, Bailey?
Bacteria.
Bacteria, yeah, gross bacteria gets in your shoes.
I basically said.
Yeah, bacteria gets in your shoes and then it eats stuff in there, sweat or whatever you got in there, and then it probably like burps or farts out stinky gas. That's how it works most of the time. Yeah. Do you know? So they have new products now. It was for a while it was only one manufacturer. Now everybody's starting to do it. But they've made new deodorant products that don't work the way other deodorants work. They actually target the smelly bacteria by making the area wherever you apply it more acidic than usual, and then those bacteria can't produce stinkiness. So it's stuff like Lumi, Mando. I think Secret is now coming out with a formulation that's very similar, but it's like they have it in stick form and lotion form. The lotion form, you can quite literally put on any part of your body that doesn't smell good. Any part, and I mean any part, because that's what it's made for. So it's straight up amazing. Yeah.
You can just use hand sanitizer, alcohol, it just kills it.
Yeah, but you'd have to be slapping that under your armpits, and I don't know if that would be, and there are other parts of my body, I'm definitely not putting hand sanitizer on like it's not happening. But that stuff, you can put it on. And one of the selling points, and it's true, it is absolutely true, it lasts like 72 hours. If for real, now it doesn't stop you from sweating, so you may have like pit stains, but it stops you from smelling, like straight up stops it,
I don't like the Lumi ads where they give stupid statistics.
Yeah.
Like, this is 10 times better
Mhm.
than just a shower alone. How can you know that?
The ads were kind of goofy, but I personal attestament, when my lupus kicked in and I got to be a human oven and all I did was sweat all day, every day, no matter how warm or cool it was in the room, like it was ridiculous for a while for me. I was like, I'm gonna try this. It works. It's not a lie. Do it. It's the best investment ever. This stuff for real works. All right, so odor production. Aside from stinky feet and stinky pits and stinky everything else, what's another example of odor production? Bailey, you got one? Vinegar, yeah, vinegar.
Vinegar and there was I did it at home with something and it created a
It stinks. Yeah. What else? Can you think of another one? Jordan?
I was thinking gasoline.
Gasoline, they actually add a smell to
Yeah.
gasoline so that you know it's there, so you don't. Yeah, they put it there so you don't accidentally set yourself on fire. Drew, what else stinks?
Oh, odor just means smell. It means bad
Yeah, it doesn't mean bad smell. You're right.
Any food like this.
Okay, yeah. So, but is that a chemical reaction or are you smelling the chemicals? That's the question. You're smelling those chemicals. What do you think, PJ? Burnt things. Great example. When you burn something, you're carbonizing. That is a chemical reaction. You smell it. James? Rotting things. Perfect example. How do you know if your milk is still good? Give it a sniff, right? Give it a little
Milk always
sniff.
smells bad.
Yeah, give it a little sniff, and if it smells sour, don't go there. Yes.
Well, I mean, unless extra milk is bad, so we really see gas, so the sides don't.
That's right. So that's the next thing. So Yusuf just said when your milk gets real bad, are we all good? When your milk starts to get real bad, it does. There are chemical reactions that release gas and that causes that little dent, that little bubble on the side to pop out. That also is there. Some people freeze milk and it allows for that expansion too if you freeze your milk. It's disgusting. It's gross, but some people do it.
What?
Not a fan of frozen milk, but. So yes, all right. So then what's this? What would this one be? She knows. Lucas?
Flour?
Not flour. Good guess, PJ.
Light production?
Not light. Jordan?
Changing in substance?
Yep. What are we creating there, Bailey?
Precipitate.
Precipitate. All right. This makes me so happy. 4 years ago, and she still remembers. So that's good. That bodes well for all of you. I hope. All right. So yes, this is formation of a precipitate. So we've done this in lab when we added something to something else, and then your mixture went cloudy. Do you remember your solution going cloudy? The reason that's not just a color change, you can see it's opaque, right? So there's particulate in there. There's solid. So that's formation of a precipitate, which is a solid in solution that will
Milk, isn't it?
fall out with gravity.
Isn't it? Milk precipitate?
I think you're thinking of like it being like a more of an emulsion or more of a or a homogeneous. It's homogeneous because all of our milk is homogenized. Because if it wasn't, you'd get it and there'd be cream on top. You know, that kind of thing.
Shake it.
Yep. Yeah, you used to have to shake it. Okay, this goes with what Yusuf was saying earlier. What would these bubbles represent? What do we think? Lucas, you gonna guess?
Oil and water?
Not oil and water. Something's forming here to show us it's a chemical reaction. Who at the back table wants to guess? Back table, James? Gas, evolution of gas. Okay. Somebody give me an example of a chemical reaction aside from the milk. A chemical reaction that's producing gas. Did you have one, Asher? Thought you did, but it left you. Jordan?
Combustion.
Combustion's a good one. You do get, yes, you do. Let's see. Okay, Chloe. Yes, they do. Vinegar and baking soda produce carbon dioxide. All right. Who else? Anybody want to take one more stab? All right, Xander.
Evaporation.
Evaporation's a physical change. What's another example of a chemical? Good guess, though. What's another example of a chemical change? Yeah.
You fart?
Yeah. Thank you. Very good. Yes, there are chemical reactions going on in your intestine with all the little microbes in your biome that live there. and they are munching away on whatever you ate and they are producing gas. That's why you are producing gas. Do you know that now in medical school, so they teach systems, right? They teach, you know, your integumentary system, your neurological system, your gastroenterological system. They are now teaching biome as a system. And they should, because your ability to have a balanced biome has a lot to do with your health. So like my doctor recently did a whole biome test on me. It was really fascinating. But one of the things that came back explained something like my B12 was really low on all my blood tests. And we were like, why is my B12 low? I'm taking the vitamin. Turned out that the bacteria that most people have that break down the B12 into what you can use, I don't have that balance right. So it doesn't matter how much B12 I take, I'm not going to get the benefit of the B12. So today, for the first time ever, I'm wearing a little B12 on my hip, which allows me to bypass my gut and get the B12 because my gut's failing me. See, this is really interesting stuff that we're getting into, like with medical technology lately. We're figuring things out. All right, so that's evolution of a gas. What might this one be? That table. Oh, Drew, yeah, temperature, change in temperature. All right. So this, we're talking about those little packets that you pop for your hands, or, you know, warm up your hands, warm up your feet, or cool off your injuries. That's probably a really good, like, accessible example of those. You've probably seen them and used them. What's this one? Ridley. Light, right? Production of light. Glow sticks. Everybody loves these, right? You crack them, they light up. Yeah, there's a chemical reaction going on, and it's producing light. I would not need them. I would not.
Yeah, that was an accident.
I would not recommend that.
Yeah.
So not fun. So not fun.
I was like
All right.
3 years old.
And
So,
one more.
explosions.
Very good. Production of sound. Yes. All right. What you gonna say back there, Colin?
Sodium and water.
Sodium and water does produce the sound. That react. Oh yeah.
Sodium.
Yeah. Pure sodium in water is a lot of fun. Potassium too. Woo. All right. So production of a sound, and this is the result of a combustion reaction. Jordan.
Like fire cracking.
Yes. Yeah. Fire, crackling, and popping. That's actually a physical change most of the time. They're not always. It depends on what's
I was
exploding.
thinking boiling.
Usually when you, well, that's physical too. But usually when you hear the popping sounds from a fire, it's because there's little bits of water in the wood and they're just expanding rapidly because of the heat. And you hear the breaking sound. But same thing with combustion, what you're hearing with the firework is you're producing a longitudinal sound wave, right? When that air expands rapidly, you get that kind of a thunder effect. James. Pop rocks. There you go. Pop rocks is a great example. The sound of pop rocks in your head. Oh boy, Drew. There's definitely a chemical reaction there, I would say. Lucas?
Fire?
Fire. Well, he was saying fire. Jordan was saying fire. And how about Ridley? Lightning. So lightning that's going to be our next one here. Lightning is when you have the production of what? Electrical energy. And that can happen with chemical reactions. But then the sound, so here's the thing, the production of the sound is a sign of the chemical reaction, but the actual manifestation of the sound is physical, right? It's the rapid expanding of air that causes the sound to be produced, but that's a sign that something occurred chemically for that energy to be released, right? Okay.
For the previous sound, my chicken burst in the microwave.
That's probably physical too. It's probably because there's water in it. It's like popcorn, right? Popcorn makes noise because there's water still in that dried up kernel. And when you expand that water rapidly in the microwave or on the stove, however you do it, it goes kaboom, right? Electric fields. Yeah, okay, there you go. All right, so these are all examples. Eel. Okay, yes. Gross. Those are cool, but gross, right? All right, so we have different types of reactions. And these are the ones that we're gonna, some of the ones, not all, but these are some of the ones we're gonna touch on next year. So first one is what we call a synthesis reaction. And it makes sense. When you synthesize something, you put things together and create something, right? So this is when you combine things to create a new thing. So a good example is you're combining sodium with chloride and you get what?
Salt.
Sodium chloride, which is salt, right? You too. Do I have to separate you?
I'm fixing my hair.
Shit, Daddy. Look at him. Quit. Leave. All right, decomposition. This is not synthesis, but the opposite. This is when you're breaking something down. So good example. Say you only drink diet soda. You figure your teeth are in good shape. They're not so much in good shape because your sodas contain carbonic acid, which is part of a standard ingredient. And what it is when the decomposition occurs, your carbonic acid breaks down into water and carbon dioxide, and that's where your fizz is coming from. So even if you're not, like, even if you're just drinking Coke Zeros all day, you're like, oh, I'm not hurting my teeth. There's no sugar. No, there's acid, which is what the sugar allows to form in your mouth, right? It's the sugar in your mouth mixing with your saliva and other things going on that cause acid to break down your teeth, right? So in this case, you're just bypassing that step and putting acid straight on your teeth.
So Dr. Pepper is more acidic than Coca-Cola or Pepsi.
Yeah, you can do pH tests on them and it's tons of fun to see.
Because what happened to one of our grandmas, she only ever drank Dr. Pepper.
Oh,
and
no.
it destroyed her teeth. But now she's drinking Pepsi and her teeth are fine.
Is she from Texas?
No, she's from Ohio.
Texas is a
Oh.
Dr. Pepper thing.
Yeah.
Yeah,
Does that mean if you just drink Coke with straw, it won't damage your teeth?
straw might be helpful, but
You
you're
still have to
still pouring
acid
acid in there, but it can help. It can do a little less exposure.
Put it straw straight down your throat.
There you go. There you go.
I want to taste
Do
it.
what? Still got acid in it. There's carbonic acid in that. Absolutely. So combustion, we know what combustion is. Anytime you burn something. That one's easy. Anytime you burn something. Single replacement. Okay, this is when you're taking out one. Do you need help with that blanket? Come here. Do you want the blanket on you? Sorry. You know, that's usually when you want. Like,
Wait, really? He becomes a little mess.
he'll completely bury himself. He's a dachshund. He's meant to be buried. Yep. All right, so single replacement is when you have one element or compound taking the place of another. So an example would be potassium, which reacts with water, and it forms a colorless solid compound that we call potassium hydroxide. So if you look here, you can see one of the things that's been replaced is one of the hydrogens, right? Yes,
It's the colorless solid. Is it basically like glass and you can see through it?
I think so. I don't know if I've ever seen it in myself. I don't think I have any downstairs on the lab shelf, but I think it is kind of clearish, like a crystal. Okay, double replacement. This is when you got your ions involved, your cations and your anions, and things are switching places. So an example of this would be sodium bicarbonate and acetic acid. What is sodium bicarbonate common name?
Salt.
Mhm.
No, salt. Baking soda?
Yes, baking soda, common name. What is acetic acid, common name? Vinegar. Yes, okay. So when you are using, I know some of you guys are using of vinegar and baking soda in your machine, I've heard. So what you're producing is carbon dioxide and water and a salt. So anytime you mix an acid and base, you're going to get carbon dioxide, a water, and a gas, a water and a salt. That's always what's going to happen. It's just kind of a standard thing. All right, so scientists classify reactions by transfers of what? When these bonds are forming, what's getting transferred? Liam?
Energy?
Yeah, but no, that's not what I'm looking for. Lucas?
Electrons?
Electrons is what I'm looking for. Yes. All right. So you get electrons that are either shared or transferred, and then you get bonds that form. All right. So you can measure the rate of a chemical reaction by examining the ratio between the amount of substance or products formed and the time it took to produce them. Products can be measured per unit time or by volume per unit time. So when we did rate at the beginning of the year, what was the ratio? Rate at the beginning of the year, we were talking about Newton's laws and movement and forces. Do you remember what it was?
Something over something equals something.
Right. Something over something gives you rate. Do you remember?
So rate.
There's time involved. It's for sure time.
Work over time.
Distance.
There you go. Distance over time. All right. So distance over time gives us rate when we're talking about, you know, how fast something's moving. But when we're talking about how fast a reaction is moving, it's going to be volume over time. Okay. Factors that affect reaction rates include, okay, concentration of the reactants. The more concentrated, the faster the rate. Kind of a general rule. You want a reaction to take place, have your reactants nice and concentrated. Temperature. Usually, the warmer, the faster. Physical state of the reactant. Sometimes you're going to want them as a solid. Sometimes you're going to want them as a liquid. Very occasionally, you're going to want them as a gas, right? Depending on what you're doing in a lab, you can do certain things with gases. And then the presence and concentration or physical form of a catalyst. All right, now, once you think back to the TEDx video, he putted the ball up the little hill, and it reached the top of the hill. There was energy in, it reached the top of the hill, and then there was energy out the whole way down. That top of the hill has a name in chemistry. Does anybody know what that little area is called? That's called activation energy. And that little, when you reach your activation energy point, you've put in enough energy to activate your reaction. Now you're going downhill, okay? So the presence and concentration of a catalyst or an inhibitor, a catalyst is a compound that is going to lower the hill for you. It's just going to like shave the hill off. So you don't need to put in as much energy at the beginning. An inhibitor is going to raise the hill for you. You're going to have to put in more energy to get the reaction to start. There are sometimes we want an inhibitor. We want to slow a reaction down. There's other times we want to speed it up. So we want a catalyst. And your body is full of catalysts and inhibitors. You function because of it. Light, sometimes things are going to go more quickly in light or more slowly without light usually. All right, so when a physical change does not go to completion, a physical equilibrium is established between the forward and reverse changes. When a chemical reaction does not go to completion, what kind of equilibrium do we establish, Emily? A chemical equilibrium is established between forward and reverse reactions. So when a change is introduced to a system in equilibrium, the equilibrium shifts in the direction of the what, Yusuf? That relieves the change. Okay, what you're trying to do all the time is keep equilibrium. What does equilibrium mean? Like, what is equilibrium?
Basically, no more they're level.
Yeah, everything's balanced, right?
It says that the relieves change.
Yeah.
Oh yeah, you caught one. Okay, very good. Yeah, that relieves the change. That's what we're looking for. So yeah, you want things to be balanced. What were you gonna say?
Oh. Wait, now I forgot.
That happens. Sorry. I try to catch people before they forget, but it happens. Yeah. So your body is constantly trying to reach an equilibrium, chemical equilibrium, physical equilibrium. I was telling the kids earlier that a good way to think about equilibrium is to think about membranes. We have a lot of membranes in our body that try and balance what's on both sides of it so that it's equal in concentration. And this one's more of a physical equilibrium, but it has to do, well, it's kind of both because it has to do with chemical concentration. So anybody know anyone? You guys are probably all too young to have done it, but anybody know anybody who's done a colonoscopy or an IVP? Yeah. What do you have to do leading up to that test? What do you have to do, PJ?
Clean your bowels.
Clean your bowels out, and they make you drink something, right?
Both our favorites of gum.
Yeah. So sometimes there's all kinds of things, but one of the things they typically make you drink is it's a salty drink. But it's like, yeah, sometimes it's a salt. There's other ways to do it. There's other osmotics that you can use that are not salts, but this is an example of equilibrium. So you drink the nasty salty stuff, and now you have a high concentration of salt inside your colon, which your colon doesn't like. So it's going to get equilibrium how? What's it going to do?
Trying to get rid of the salt by
But it can't get the salt out. So what's it going to bring in to balance it?
not salt.
Water. Yeah, it's going to bring in water from elsewhere in your body, which is why they're like, drink a lot. So you're going to absorb tons of water into your colon to try and balance out the salt. And then you get the result that is desired, probably not by you, but by your GI doctor. Right.
I
Yeah.
heard someone say it was like X-Lax and taco mix.
Yeah, that's a good example. Yeah. All right. So little preview of carbon and nuclear chemistry. We are just touching on these. All right. So for nuclear chemistry, some elements naturally change into different elements. So for an element to be different, it must change the number of protons in the nucleus of its atoms. That only happens in radioactive elements. Protons, Ridley, you good? All right, protons. So if you change the number of electrons, what do you have? An ion. If you change the number of neutrons, what do you have? Bailey? An isotope. If you change the number of protons, what do you have? PJ? A different element, right, exactly. Okay, so it's only these dudes down here. These nuclear ones that we think of as radioactive, right? These guys, all right? So unstable nuclei in radioisotope. A radioisotope is going to be a radioactive element that has a different number of neutrons, right? They can get unstable and they undergo what we call radioactive decay, right? And in a nuclear reaction, it is a nuclear reaction in which one of the elements changes into another. So you will literally change into a different element. That does happen, but only with these guys. So nuclear energy is released in nuclear reactions. The two types are going to be what? Fission and fusion. Fission means you're doing what? Yeah, and well, fission means you're taking them apart. Fusion means you're putting them together. Right. Okay, good. All right, so carbon chemistry. What do we call compounds that come from living things or are produced from living things that contain carbon? Caitlin? It's there, it's not there.
Living.
Oh, if it came from a living thing. Oh, your brother just stole your answer. Yeah, say it louder, James. Organic compounds. These are our carbon compounds. Okay. Is glass organic? No. What's glass made of? Sand, silica, right? Okay. Is wood organic?
Yes.
Yes. Is paper organic?
Yeah.
Yes. Is now here's a question. Is a rock organic?
Depends on the sometimes.
Which rock?
Say it louder.
It depends on the type.
For example,
Limestone.
What he said.
limestone. What's another one?
Obsidian, those magma rocks.
There's certain.
Those are usually
Sedimentary technically could be organic because it could have
right.
bone matter from fossils. in it.
Correct. How about coal?
Yes.
Yes.
Coal is what?
Organic.
Organic, right? Okay, so
Diamonds, but-
yeah. Uh-huh.
Obsidian could be organic if someone fell into a volcano and then
There you go. Obsidian could be organic if someone fell into that. Yeah, okay, that's true. People were sacrificed into volcanoes. You're correct. All right, so hydrocarbons. Hydrocarbons are compounds that only contain carbon and hydrogen. They are the simplest type of your carbon-based compounds. The smallest ones have only 1 or 2 carbons, but large hydrocarbons have hundreds. They're big, long chains. Yes. And the size of hydrocarbon molecules influences their properties. Some are itty bitty, some are really big. And as a result, some are gases at room temperature, some are liquid, some are solid. Hydrocarbons, we will talk about them next year. And they are obviously important in biological stuff because we're talking about organic stuff. Hydrocarbons are generally non-polar, which means what? Bailey?
They don't have a north or south pole.
Yeah, they don't have a charge. Yes, they don't have a charge. And they tend to repel water. What is a good example of something that repels water, Jordan?
Oil.
Oil. So we know that oil is
not polar.
organic. What's oil come from?
It depends on the type.
Which oil? Vegetables.
Vegetable oil is a good example. Yeah.
Baby.
Yeah. So oil, most of the time we're talking about oil that is in essence organic, right? It came from something organic.
Baby oil.
They don't dissolve in water. So we separate them into saturated and unsaturated, and the classification is based on the number of bonds. Yes.
Unrelated question, is baby oil considered murder?
No.
Murder.
I mean,
It's
baby oil.
Baby oil.
It comes from baby.
It's not made.
Oh, it didn't come from the baby. No, it's for the baby. But that's a great question. How many babies did you have to squeeze to get that bottle of baby oil?
Baby don't produce oil.
Yeah, you have to squeeze them real hard. You might get a drop or two, but that's pretty gross. You get a baby juicer. I mean, y'all, you're crazy.
That's a baby farm.
Yeah, baby farm.
Someone
Yep.
came up with baby juicer.
Baby juicer. I did. I said it. You good at the back table? Okay, Lucas, did you have a question?
Something that occurs to me. So,
Shh, hang on. Lucas had a thought.
so photosynthesis,
Mm-hmm.
that it's, if photo is light,
Mhm.
and then synthesis means like it uses it, like.
Correct. Using light.
So, would that mean like, so hydro means water, right? So could you have,
Water or hydrogen, depending on how you're using it.
so could you do hydrosynthesis?
So you can do, yeah, you can. You can also do hydrolysis, which is the exact opposite, where you're breaking down the water molecule into its constituent parts of hydrogen and oxygen, which we will do next year. We will produce We will take water and we will break it down and produce 1 tube full of carbon dioxide. I mean, 1 tube full of hydrogen and 1 tube full of oxygen. And it's really a lot of fun. But yeah, technically you can't do that. It's gonna require a lot of energy.
I looked up why Clorox is named Clorox.
Well, why? Tell us. We wanna know.
Cause it started using chlorine, but then it switched to different.
There you go.
chemicals.
Okay, so because we know that Clorox has no chlorine in it because we looked it up.
Anymore.
Yes.
So hydrocarbons are non-polar,
Mhm.
so that means that they can't have covalent bonds?
No, because there are covalent polar and covalent non-polar. Those are the 2 types. There you go. All right, so let's have a look at the next thing. Here are examples. So we have carbon compounds and we break them down into carbohydrates, lipids, nucleic acids, and proteins. So your carbohydrates are things like starches, sugars. They're only going to contain carbon, hydrogen, and oxygen, and they're used for things like energy and structure. Your lipids are things like fats and oils, and they still only contain the same thing as your carbohydrates. They're just arranged differently. It's carbon, hydrogen, and oxygen. That's it. And these are things like your cell membranes and then energy storage. Where are nucleic acids found? Where are nucleic acids found? James, DNA. There you go. And RNA. So nucleic acids form nucleotides, and look what's in them. We've added 2 more elements. What have we added?
Nitrogen and potassium.
Nitrogen and not potassium, but
Phosphorus.
phosphorus. Okay, and this is where you get your storage and transmission of genetic information. And then we have our proteins, which are made up of amino acids. And look, we don't have any phosphorus over here, but we still have carbon, hydrogen, nitrogen, oxygen. And these are enzyme channels and structures. All right, the most common elements in living things. Who can give me some or all? James. Carbon's the first one. Hydrogen, he's got it. Nitrogen. Oxygen. Yes, one more. One more.
You said sodium.
No, it's not sodium. He knows what I'm looking for. That's why he's trying to pull it out of the recesses of his brain from 3 years ago.
You were here for,
He was here for bio.
bio, yeah.
Mhm.
I have no idea.
Hang on. What is it? What is it? Hot fly, Drew.
Silica?
Not silica,
Calcium?
not calcium.
Sulfur?
Sulfur. There we go. Good job, James and PJ. Nice work.
No.
Schnapps. There it is.
Schnapps.
Schnapps is a thing. Schnapps. This is what we say. We say schnapps for real. Like schnapps is how you remember that these are your most common elements in living things. CHNOPS. You can remember that. That's going to help you a lot in biology because they will be there frequently. Just remember schnapps. You did biology. Yeah. Schnapps. Yeah.
Why is this text different from each of the
Because
others?
they just came from different periodic tables.
For fun.
Yeah.
It's just for funsies.
It's
So then you have things like the carbon cycle. You probably see it. Truly wrong. You carry his blanket all the way in there. Sorry. Nothing distracting, nothing to see here, just a dachshund uncovered in a blanket running around the house.
I feel like a ghost. Oh, you should dress up as a ghost for Halloween.
Yeah, we could do the little Nightmare Before Christmas ghost. All right, so
Zero.
yeah, there you go. Yep.
Everyone loves zero.
So we have, thank you, Jason, for returning the blanket. This is your blanket.
You took it with you. Sadly, still wanted it.
Mm-hmm.
It's like that's.
So our carbon cycle, thanks for the distraction, Oswald. The carbon cycle is, we have lots of these. We have a carbon cycle, we have a nitrogen cycle,
Water cycle.
and we have a water cycle, right? Our Earth works with cycles. So if you look here, this carbon cycle is exactly what people are referring to when they talk about the size of your carbon footprint. That rabbit is dead. Death and waste.
Oh.
Okay. Yeah, this is about what is your carbon footprint is basically this part right here where you see this dead rabbit, death and waste. What's your death and waste? How much are you eating? Right? So remember that this is important. Carbon is important for all life and the cycle in general is what keeps all life going. All right, now let's have a look at our review. Let's do a little review, shall we?
Yes. Yay.
All right, let me switch whoops, screen share to. What's this, y'all? That's you.
Your job, a pocket shop.
All right, so for this review, we're gonna do this team and we're gonna do you two and that group as a team. And every time we have a box to reveal, I'll alternate teams and y'all just give me the answer as a group, okay? All right, so let's do it. You guys first, what is it?
No. Yes. Scientific.
We agree? Scientific method is your organized plan for gathering, obtaining, and organizing information. All right, team two in the back. Scientific law says what? James? It says what happens? A fact. Team in the front. Scientific theory says what? Why it happens? A what? An explanation. I'm not huge on memorizing things because I really think it's more important for you to understand the processes deeply. Memorize. Whoop, that came too early. Whoop, no, it didn't. Memorize, memorize, memorize. That is an easy one to memorize. The scientific law tells what happens at fact. The scientific theory tells why it happens in explanation. Yeah.
Okay, I remember it's theory and why both have Y's at the end.
Theory and why both have Y's at the end. It's a good one, PJ. That works. All right, who am I on? Team in the back?
Yes.
Okay, we got 3.
I bet sure.
Can you give me any one of the 3? This is why is science never settled? James, give me one. Yes, because that's an incorrect statement that science is settled because it assumes science is in a binary state and that it magically crosses over some line when it is no longer in a binary state. Okay, who can give me number 2? Another one over here, this group. Oh, Bailey, you want to do it?
Natural science isn't about 100% proofs. It's about like narrowing uncertainty.
Narrowing uncertainty. That's the big one, narrowing uncertainty. So we have not binary, narrowing uncertainty, and then what is, oh, wait, that's not the one I want. What's the next one? Right, or vice versa, that a good understanding in one area means a poor understanding in one area, or a poor understanding means a good understanding, and a good understanding means a poor understanding. It has nothing to do with each other. Our depth of knowledge in one area of science does not apply evenly to our depth of knowledge in another area. It's just not the same, right? Some things we really understand, some things we for real do not. Thank you, Yusuf. All right, who's up now? Team in the front. An observation is made by using what?
Senses.
Senses, your senses. You observe using your senses. What's an inference made by? Asher, do you know? Yeah, and also including what? Prior knowledge. That's where you need to know. Prior knowledge and experience, right? So know the difference. Those questions are going to be on your exam. You have to know the difference between an observation and an inference. Yes.
That was the only function I messed up on.
On the midterm?
I almost got 100.
Well, now you know. Now you know you'll come after it. Okay. Now we have our laws of conservation of energy and momentum. Who is up? You guys are up in the front?
Yeah, we are.
All right. Somebody give me law of conservation of energy
Energy cannot be created or destroyed, it just changes shape.
or form. Yep, you got that. All right. And how about momentum, back group? Oh, Colin?
Same thing, you can't create it or destroy it.
Okay. All right. So if no net force acts on a system, the total momentum of the system doesn't change. This is the one that's a little different. Whereas like mass, matter, and energy are all plug and play. Energy, mass, or matter can neither be created nor destroyed. It can only change form. But when you get to momentum, it's a little different. So if no net force acts on the system, total momentum of the system doesn't change. So this would mean if there was no friction, the ball rolling down the road would continue rolling down the road at exactly the same rate it is currently rolling down the road, right? But friction is going to change that because that is acting on the system. All right, how about Newton's first law? Who's gonna do it? Caitlin, you wanna do it?
No.
No. Yusuf, you wanna do it?
Action, reaction, is that all?
Is it action reaction? Is that the first law? PJ?
If an object is in motion,
Yeah.
it stays in motion unless acted upon by an outside force.
Yes, object in motion stays in motion, and object at rest stays at rest. Unless acted on, yeah, see, I put these same pictures from the slides when we went over this, so that you could kind of flash back and get the little image in your head of the little, Renaissance rat flying. Yep. Now, that group, second law. James.
Which was that?
Yes, this is at, yeah, rate of change in momentum is proportional to the force applied, or F equal, if I were to ask this question, explain or tell me what is Newton's third law. If you wrote F equals ma, I will accept that, because that is the formula that says the rate and change of momentum is proportional to the force applied, because you have F on one side of the equal sign and your momentum, sorry, on the other side, acceleration, sorry, on the other side, my brain died. All right, third law, who's up? Liam.
Every action has an equal and opposite reaction.
Every action has an equal and opposite reaction. He's gonna kick the ball, it's gonna come back and kick him in the face, boom, right, there you go. All right, now, if there was no friction, it would be a guarantee that it would come right back to his face, right?
Yeah.
But it's gonna lose momentum because it's being acted upon by an outside force.
And
What you got?
I found a brownie point. And it isn't capitalized in the other two R's.
Oh, yeah, maybe.
no friction or gravity.
Yeah, gravity too.
Miss Danny, I think you have a question.
Yes, question.
So I saw this videos in which the people do like, they have the bowling ball and they just let.
Yes, the professor, I put that, I think, in one of our
Yeah.
resource links.
They-
Yeah, he has that whole bowling ball, he stands against the wall, he pulls it right to here and he lets it go and it's a pendulum and he just stands there and it comes to like
Oh,
right
yeah.
here, he goes back. Trust the science, man. That's putting your faith in science, because woo, I mean, I know it's not gonna hit me in the face, but I would still be too terrified to do it. I'd be afraid that I didn't drop it, that I gave it a little nudge, because a little nudge is gonna change it, right? Dropping it's one thing, nudging it's a completely different one.
Yeah.
All right, Pascal's principle, who's up? Back table?
Back there.
All right, what's it gonna be? Do you know it, James? It is force.
Equals.
You want help?
Over A.
And, okay, Drew,
Pressure equals force over area.
pressure equals force over area, but what's Pascal's principle exactly? That's your pressure formula.
It's like a balloon.
Yeah,
Asher needs me to call on him. What is it, Asher?
Pressure is equal to pressure.
Pressure, there you go. Okay, a change in pressure to any point in a fluid is transmitted equally and unchanged in all directions throughout the field. Okay, very good. That's a big one. Bernoulli, who can do Bernoulli? Jordan, can you do Bernoulli?
The amount of speed the air is moving at, the less pressure is in that area.
That's pretty much it. So yes, the speed of a fluid increases. As the speed increases, the pressure within the fluid decreases. And he's got his little atomizer there. Right, that should help you remember. Excellent. It's a zip it. Pascal's principle is at work in what kind of systems? Sure. Hydraulic systems. Okay, where would you find a hydraulic system at work in industry or business? Asher? Plumbing, that's a good one. Where else?
Hydraulic presses.
Hydraulic presses, great. Where in a life form would you find a hydraulic system? Sea stars, yes, they have a water vascular system that uses hydraulics to move their little arms about.
Combustion engine.
Huh?
Combustion engine.
That's not a light.
Oh.
There is actually, that is, because that's gas. Yep, yes.
Some computers might use like water to cool down.
Yeah,
their
some
things so
do.
They don't overheat.
James?
Yeah.
Do what? Elephant trunks. Oh, do they use hydraulics? Oh, that's pretty cool. I know they use muscles, but they probably, yeah, they probably do. That is pretty nifty. Octopi, same kind of idea. So there was, we saw a car, when did I see it? Like a week ago? Did you see that car that clearly bounced? It was one of those bouncing cars. It was driving down the road, but I knew it was one of those, but you could see the hydraulics like behind the wheel. You know, the ones that they go boom,
Yeah.
boom. Yeah, it was one of those. That was cool.
Like from cars.
Yeah, yeah. All right, Bernoulli's principle explains what concept? Front group. Somebody tell me.
Lift.
Lift. What's he playing with? Okay.
Airplane design.
That'll help you remember. Lift. Huh.
Wasn't the airplane invented after Bernoulli?
Of course it was.
Obviously. They had to
Did you
use
remember?
They had to use the concept to do it.
Mhm.
Yeah, but why is he holding an airplane?
So you remember.
Yeah, just that.
It just-
That's not a Bernoulli.
They're rats,
Yeah.
they have clothes, whatever.
They harnessed fire.
It's AI.
I love it.
It doesn't matter whether.
So,
Oh,
what is described as a force distributed
Not-
over an area?
Pressure.
Back tape. Okay, pressure, you're right. And the unit for measuring pressure is front group. Front group, Pascal. Pressure is the Pascal. Remember our little French rat, little Blaise Pascal and his cute little cradle and the adorable, yes. All right, a push or a pull on an object is a what? Back table. Ridley, no? A push or a pull, they're arguing about elephants. A push or a pull on an object is what? Drew, it's a force. And what force is measured in?
Newtons.
Front table, Newtons. All right, very good. He's got the Newtons in his hand to remind you.
No, he says they're pop tarts.
Those are not Pop-Tarts. What is wrong with you? Have you seen, yeah.
I'm saying it's about him. I'm telling him it's a big piece.
Y'all are killing me today. Puberty, Pop-Tarts, y'all are baby boiling. I don't even.
Really deformed.
He's the one saying it's pop tarts.
Y'all are just bizarre.
Yes, I have.
The force that opposes. The back table, the force that opposes the motion of objects that touch as they move past each other is true. Friction. Y'all are missing the review because you're talking about elephants. Okay, that's right. Friction. Okay.
That's a good reason to miss for movie.
Is it feeling punchy? Is it just me?
In Collins,
I
we're
know.
going to argue about animals.
Elephant. I admit that I do not know the intricate workings of elephant proboscis, but I do know that there is musculature at work beyond that. All right. What is the force that acts between any two masses? Front table, front group, whatever. Gravity. Yes. Okay.
That's a big rat.
Yes. Now it's perspective. We're close to him. Earth is far away. That's right. Heck yeah.
Sure.
The speed and direction in which an object is, which object is moving, it should say, is its,
Vector.
no?
What?
Velocity is, yeah. Vector is the, yeah. That's how we discuss it, but the speed and direction in which it's moving is its velocity.
Isn't all the acceleration?
The acceleration, and you get that squared in there, right? Because you're adding time in, like time over time. Remember seconds squared or time times time, really?
Acceleration is how quickly you get up to speed.
Mm-hmm.
This is the rate you continue at.
So front group, the ratio of the distance an object moves to the amount of time the object moves, is
This
it?
is acceleration.
There you go. This is, it's speed, sorry, it's speed, right? And remember, speed is a rate. Like-
Speed is in a direction.
Yes, the direction is when you're getting what?
Velocity.
Velocity is when you're getting direction in there. If you're just doing speed, you saw my shirt today. Distance raptor over time raptor equals velociraptor. It's cute. All right, what is the rate at which velocity changes? That's your acceleration. So you have your velocity, you have that's your direction and how far you're going in a given unit of time, and the rate at which that is changing is acceleration. Drew.
Why is he wearing a spacesuit, gets out of a Huracan and can't even reach the pedals?
He can reach the pedals because it's his Huracan. That's a race truck.
Nothing makes sense in that world.
That is
I was about
that's a racing suit. It's a fireproof racing suit.
Astronauts freeze there in that.
I mean, for real, he could crash. He needs his little fireproof
None
suit.
of the laws
I would
here
like to say somehow
apply
the way that this
there,
is stuff
except
just
the ones
looks
we are
like-
talking about.
He's cute. I love him. So when riding a Ferris wheel, you're guaranteed to experience what? Is this back group, front group? Where are we? Front group? Okay. Not guaranteed to vomit. PJ,
Oh, depending on the person.
you might feel sick. What are you guaranteed to feel? Bailey?
Joy, whimsy, and something else.
Joy, whimsy, and something else, yeah. Total boredom, acceleration, buoyancy, or electric shock. You're guaranteed to experience acceleration, though it might be totally boring.
Electric.
Hopefully, you're not going to experience the electric shock. But you are guaranteed to experience acceleration is the one that's underlined. So if you see these other answers in your multiple choice, though you might experience them, you're not guaranteed, right? Some of you hope you don't experience. Definitely not buoyancy, right?
Yeah.
All right, now we have Watson and Jules here. Remember on your card, you can write down the formulas that relate to these things, but you cannot write like this little, I wonder what Watson had to do. You can't write that, right? You can't do that part. You have to know what watt is, like what the unit is. So Jules is the back root. Back root. It takes a lot of hard what, Ridley? Work for Jules to mine is Jules. I wonder what Watson had to do to become the most, Lucas, powerful rat in the world. So the watt is our unit for power. Joules are our unit for work. Very good. All right, what is the ability to do work? Is it back root now? Back root. Colin? Energy is the ability to do work. If you don't have enough energy, you can't do your work. Simple. And what's the transfer of energy? Front group. Heat. Work, technically, heat's the transfer of thermal energy. Okay. Thermal, but energy to do work, energy is the ability to do work, and then the transfer of that energy is work, right? It's a little crazy, but that's it. Light travels in two ways. It travels as a blank and also particles. Okay, what's the first way? Back group, Drew?
Wave.
Travels as a wave and also particles called photons. If you see this question, read it carefully. Carefully. It might be a true or false, and it might have a word in it wrong. Don't just be like, I know this, and check it, because it may not be written this way. Clue, foreshadowing.
Oh, okay.
All right, when combining equal amounts, red, green, and blue light produce what? Front group? Caitlin? You want your coins, babe?
Colors of light. White.
Yeah, when you read, they're the primary colors of light, and they combine to produce what kind of light?
Look at the colors or the
Yeah, when they combine.
yellow, magenta, and cyan.
No, when you put all three together, you're gonna get, yeah, she got it, white light. You want these?
No, I don't use them.
No? Okay, but I'm back to the group. All right, white light. So when you put red, green, and blue together, all together, you get white. If you put two of them together, you get a different color, but if you put all three together, you get white. Remember that red, green, and white, and red, green, and blue are the primary colors of light. What are the primary colors of pigments? Somebody just say it.
Red, yellow.
Red, yellow, blue. We know this, right? This was like kindergarten. Okay. All right. What is well above the range of human hearing? So we're talking about sound. What kind of sound? Back group. Ultrasound is well above the range of human hearing. Okay. In case you did not see that. Ultrasound. All right. Front group. The distance from crest to crest or trough to trough is what? Liam.
Wavelength.
There you go. And back group, the number of times the same part of a wave passes a fixed point in a given time. What is this? What, Colin?
Frequency.
Frequency. Now remember, this is important. Remember that wavelength is involved in your perception of color, and frequency is involved in your perception of pitch. You're going to need to remember that, okay? So which is a better conductor of electricity, distilled water or salt water? Front group, salt, because it contains ions. I have it written there, sorry. So you're going to need to understand that and explain it. You have the ions in salt water. That's going to help electricity be transported faster. All right, now you're going to need to describe for me, potentially, might be a bonus question, maybe. It's one of the great smackdowns that we discussed in Q3, okay? You're going to need to tell me the names of the people involved, and the methods that they used, who was participant, why was there a feud, how they win it. Somebody tell me one. There were 2 great SmackDowns. Somebody tell me one.
One
Somebody-
was like the frog hanging thing, I forgot the name.
Yeah, that's not gonna help you. What's it?
Thomas Edison and I forget the other one.
We're
It's
getting there.
the-
You got the name?
Oh, well,
Nikola Tesla. Okay, what about Thomas Edison and Nikola Tesla? Liam?
They were trying to see if alternating current or direct current was better.
Correct. Who was supporting direct current? Edison. Who was supporting alternating current? Nikola Tesla. Where do you find alternating current now?
Everywhere.
Drew?
House.
In your house. Where would you find direct current? Drew? Battery. Good example. Okay, now. They were fighting. Who did Tesla work for? Caitlin?
George Westinghouse.
Westinghouse. Who did Edison work for himself, right? Okay, tell me some things that happened in this feud. What happened? What happened?
Nikola Tesla used to work for Thomas Edison.
Mhm.
He didn't believe, like, he didn't believe in Edison's theories, so he went to work for himself. With the
Yeah.
help of George Westinghouse.
Yeah.
And,
What are some things that happened? Lucas, do you know one thing that happened? Any one thing?
They electrocuted an elephant.
Who did?
People.
Who electrocuted the elephant?
Thomas
Edison.
Caitlin, yeah. Edison, why did he electrocute the elephant? With what?
The DC
to prove that it was
Yes. What did he use DC or AC to electrocute the elephant?
AC.
AC, because he wanted to prove Tesla stuff was dangerous. Who largely won the feud?
Thomas Edison.
Tesla.
George
Kind of
Westinghouse.
depends on how you look at it. Yeah, I mean, Tesla won it as far as what gets plugged into your house and everything like that. Yes, very good. But Edison what was Edison better at? What did he do well that Tesla was really terrible at, really?
Giving it to the general public.
Yes, marketing. Edison was an expert at marketing. He was the king of marketing. And Tesla just wanted to do his work, right? What happened to Tesla's laboratory? Ridley.
It burned down.
Who is suspected?
Thomas Edison.
Yeah, okay, very good. Where was Tesla's laboratory?
New York,
Nope.
Boston.
Do you remember?
Jersey,
Nope. Do you remember?
then,
Close.
wait, no.
Colorado Springs. Where was Edison's laboratory?
New Jersey.
New Jersey, yeah.
Yeah.
Menlo Park, New Jersey. Where's Tesla from?
Serbia.
Serbia. Very good. All right. What was the other great feud in science? What was our other SmackDown? Who were the participants, Drew?
Galvani.
Galvani is one, correct? Galvani versus Volta, right? Okay, what did Galvani do? Yeah, really?
To figure out he could use electricity to reanimate frog legs and
Yes. What did he call that kind of electricity?
bioelectricity.
Bioelectricity. He made up his own form of electricity. He thought it was a fluid secreted by the brain, right? And then Volta, what did Volta create?
A battery. It looked
Like the battery, like the first, like real usable battery. But who made, guys, stop, you two are too chatty. Who made Galvani's ideas public knowledge?
His nephew.
His nephew, what was his nephew's name?
Nobody knows.
Aldini, and Aldini went along and galvanized all kinds of things. What did he galvanize?
Human.
Lots of animals and a human. Yep.
Yay.
Was criticized and most unlikely killed his wife.
Well, he may have,
without-
we don't really know. He may have killed his wife and daughter. We're not sure. That's what he was
But
convicted
there's
of.
no proof.
How was he executed? By what?
Hanging.
By hanging. So that means like, a lot of his nervous system is still intact, right? At least from here, wherever your spinal cord is severed all the way down, is still intact, can still transport signals. And he popped some electrodes on him, and what happened?
His left eye opened, I think.
Well, you put him on his face, yeah, we made faces.
And then he sat
He
up.
sat up, dude, sat up. What book kind of reflects this whole situation? Frankenstein. Very good. If you can give me the narrative of either one of those stories, it could be worth something to you. Okay, I will tell you this, there is a bonus question on your test that's different from anything you've had before. It's called a lab practical. You will have to get out of your seat and go look at either something, some phenomenon that I will have set up, and you're gonna have to explain how it works. So be prepared to do that. It's a little different. Yeah.
Nikola Tesla had OCD.
And a gambling problem too, right?
A lot
Yeah.
of
I
OCD.
have two things.
Yep.
One, if we say both of the great science smackdowns, will we get extra?
Nope, just one or the other. Pick one. Pick one and learn it really well.
Can we do half keto?
Nope. Yeah.
It's in the movie.
Mm-hmm.
They show him like constantly readjusting his chair.
Oh, I believe it.
and stuff.
Yeah. So the more details you can give me, listen, the more details you can give me, the more points you'll get. All right. Get one story, learn it inside and out. All right. The process of transferring charges between objects that touch is called what? Where are we? I mean, no, front group.
Static electricity.
No, transferring when they touch. Back group.
Conduction.
Oh, there you go. Conduction. That's what we're looking for. All right. What kind of circuit has only one path?
Series.
Back table.
Yeah, on their mind.
Only one path. Milo. Yep. And what kind of circuit has more than one path or two paths? Parallel. Okay. Remember those little diagrams we did that look kind of like these? Be prepared to do one.
I like them.
Okay. Be prepared to do one on the test. Tell me what's going to light up. All right. With what opposite poles attract and like poles repel? Magnetic something.
Magnetic
Field.
Magnetic force, magnetic fields. Yeah, magnetic force is what we're looking for. All right. Who's this dude?
Dimitri Mendeleev.
Back table?
Oh man.
Back table? Who's the dude?
It's
That's
Mr.
Dmitry Mendeleev.
It's Mr. Beardo.
It's Mr. Scary Santa. He's the scary
That-
Russian
That's
Santa.
Santa's cousin.
Yeah, it's Santa's Russian frightening cousin. Yep.
No,
He just
that's.
looks like the kind of guy that is really easy to disappoint. You know what I
that's
mean?
what
Like,
you- that's
you
what-
don't make the bed right, or you load the dishwasher wrong and he chews you out. Doesn't he look like that kind of guy?
That's the
Yeah.
Just me.
That's what happens if a dyslexic kid writes Satan instead of Santa.
That's right. There you go.
I'm disappointed.
Yeah. All right. So what can occur when thermal energy is absorbed or released? This one is phase change. Remember, you're talking about physical changes. Energy is absorbed or released. So think about this. If an ice cube absorbs energy, it's going to melt, right? If water releases energy, it's going to freeze, right? Okay. So boiling and evaporation are both types of what?
Physical reaction.
Physical.
It is, but what specifically? Boiling and evaporation?
Thermal.
No, I'm looking for the word that are the same. Yeah.
Physical change.
Conduction?
Hmm.
No, conduction.
How about vaporization, gang? All right, so boiling and evaporation are both types of vaporization. Vaporization meaning you're going from a liquid to a gas, right? Color change is a clue that what's taking place?
Chemical
It
reaction.
just did it. Yep, same flipping picture. We just did it, right? All right, be able to give a clear example of how each of the following is observed in everyday life. Newton's first law. If you have lab 9 still in your binder, and you should, go look at it. It had all the examples. If you can't remember it, go look at the YouTube. It's there. Okay, go find it. We did it. I made a video of it, so you could go back and look and go, oh, look, there it is.
Yeah.
Right? You're going to need to give me Newton's first, second, and third laws, examples. And I need a specific example, like not, if you say to me, you see Newton's first law in a car accident, you're going to need to tell me how, where in the car accident is Newton's first law? Like, it's when you stop, right? It's when you suddenly and abruptly stop that you get jerked forward.
And the guy flew through the windshield.
What?
What?
I don't want to know that. You're gonna need to be able to read, understand, recreate, whatever, one of these circuit diagrams. You're gonna need to label your variables. You guys know this one. This is the same graphic that's been on every test since God knows when. You're going to need to be able to label your units, meaning King Henry died unusually drinking chocolate milk. Do it. You're gonna need to be able to diagram. Look at the lever. Okay? Shh, shh. you're gonna need to tell me input arm, input force, effort, and fulcrum. I need to see it, okay? You can do it. These are the formulas you're going to want. Put them on your card. If you got your little index card and you're writing it out, I would be doing it with these slides. I'd be writing this out because these are the ones you're going to need. You have a whole page of problems on your test. Yes.
How much, is there any like specifications for the card? Like,
Yeah, it's in your email.
How
Mhm.
big is supposed?
3 by 5. You can write on both sides. You can write formulas.
Is
You
it
can
one paper or multiple?
one 3 by 5 index card. You can write your formulas on it. You can write your triangles. You can write out what it means. Like you can write out that V is velocity, A is acceleration. You can do that, but you cannot write out King Henry died Monday. You cannot write out Jules had to work really hard to minus Jules. You can't do those. You can just do formulas, okay? Like here you got delta X equals XF minus XI. You can do that, okay? That kind of stuff. Here are the other ones. You're gonna want to tell me about mechanical advantage for levers, input over output, input arm distance over output arm distance, all these things, mechanical advantage in general. Know how to do that. You guys know that every slideshow from this class is in your Dropbox, right? You can go through every one of them. And nearly every class is on the YouTube, though a couple like had issues. Yeah.
Is the final review in the Dropbox? Where is it?
Yes,
exactly?
it's in your Dropbox in your resources folder. Yep, there's this. There's one without answer reveal that just has the answers, and then there's Jeopardy. Okay, it's already all there. All right. Average acceleration, know that one. Hey, you see this right here? What is gravity due to acceleration?
What?
It's a standard. It's G. What is G? 9.8 meters per second squared. Know it. Don't guess it. Just know it. 9.8. You cannot write that on your card. That's a value. You can't give me a value, right? You can't give me a value. You're gonna have to know that value. Okay. So start studying now if you haven't already, especially since your schoolwork gets really light for this last week. Okay. Start studying. If you have questions, let me know. Otherwise, you're good to go, gang.
Thank you.
Yes, yes, sir. Yes, sir.
Remember last week you said you poured alcohol in your car?
Yeah, if you really wanted to, it would be terrible, but yeah.
The exhaust, if you smell the exhaust, that will smell like corn.
It won't smell like corn. It really won't smell at all.
Excuse me?
Yeah.
I also vanilla folder on there that I was supposed to give you.
Yes, and I've started working on it. I didn't quite get it finished, but I will have it in time for somebody to scoop it up tonight. I'll text your mom
Thank
and I will leave it on the table on the front porch. Yep.
Just making sure that. I
Yeah,
didn't
no, you
lose it.
did give it to me and I did see it.
Yeah.
And I think the one that I mailed in got lost because,
Yeah.
did you hear about the postal service issues? There's like, the postal service is like failing all of Atlanta right now. Like all of Georgia and Metro Atlanta is being completely messed up.
Oh, that's unfortunate.
Yeah, there's a problem. Yeah. Just cover it and heat it up. So it had some people come, some people come in like in the t-shirt. It's really
You can't stand up.
He said.
Yeah, it's impossible to stand out because everybody is standing out. Yeah, we have a whole group of doctors that show up here. They-
What do you mean?
They come in and you're like, whoop, they're here to park. Just put it on a plate.
My friends?
Yeah.
I tried that and it was,
Towel,
I tried that. and it
cover it with a damp paper towel. What kind are you eating? There's, no, there's a one with ham and then there's
Yeah.
one with bacon and pepper.
Yeah, no, the hair one.
Just cover it. Do
I know I did.
it again. You failed.
It's not, it was always, like, the whole city was.
Tell him about the dismounts in your session. I was telling him about the dismounts in Cleveland in your session. It was ridiculous. Kazamatsus and
Oh, yeah.
soup layouts. It was insanity.
Good.
Yeah, it was wild, but
College.
the Gen Ed, yeah.
That's, we saw them on my, there's a live stream.
What is this?
Do you know that Western's live stream the whole meet? And he's instead of months. Yeah. No, Eastern's only streamed Gen X. They didn't stream the rest of the meet. Western streamed everything.
I saw my friends stay, he did.
Yeah, you're Gen X, yeah.
Yeah, one of my friends, they,
Yeah.
Sidebar was great, because everything else was awful, he fell from everything.
He fell over. Who? Which friend? Nate?
Yeah, we have a couple that I like that work out with us.
Cyber was great.
What do you do?
It's Concha, Wyler, and double white.
Oh, I have a little couple over here for you.
All day.
I still give them to her.
All day.
Are these all yours?
James.
James gave his. Okay, well, I'll stick them in here. There you go.
Miss Danny,
Yes, Dave.
I'm applying to UGA for dual enrollment.
Yeah.
I would love a letter of recommendation.
Sure, email me, to my lab rat's email, and tell me exactly what you need and who it goes to.
Okay,
And I
so
will-
the way it works is that I give your email to UGA. and
That
then
works
we-
too. That works too. We've done that, I've done that before too. So no problem, absolutely my pleasure to do it. Yay. Love it, love it. All right. Put their names on the. Yes, sir. I think you now have 22. Womp, womp, womp. The question is, will you make it? Probably not, but you're trying.
Will it carry over to next year?
Nope. Different people, different year. Life is tough.
I got punch and Brandon Quinn's email.
Ah, okay, I'll be real careful in editing it then. But I'll probably miss things.